Thank you. Do you want to wait for Tom before we start, or? Okay, because I see people still come in, so. Okay, so thank you very much for inviting me to your seminar. It's it's not only an honor, but I know that it's going to be a challenge because I'm speaking to a diverse group of audience. I know that for some of you, some of the words here are not very clear, and I'll try to do my best to so that we're on the same page. So, and feel free to ask me during the talk whenever you feel something is misunderstood. Just stop me at any time. And it's also a challenge because they now fed me a very nice meal at the cafeteria, and I hope that we'll make it. Okay, so this is joint work with Jean Katsevich, who is a math major senior here at Princeton University, and his father, Alexander Katsevich, who is at the University of Central Florida, who started collaboration very far along in the project. So what we're discussing is a problem in covariance metric estimation for a particular problem in imaging in structural biology called cryo-electron microscopy. And first I would like to describe what is cryo-electron microscopy. And so we know what is the problem we're trying to solve. And for those of you who are expecting random matrices, don't worry, they will come, but they will come in the second half of my talk. So so if you only care about random matrices, you can go asleep, and I'll wake you up when needed. Okay, so what is cryo-EM? Cryo-EM is a technique for finding three-dimensional structures of molecules that cannot be crystallized. So many of you perhaps know that X-ray crystallography is the most known, and maybe in the last few decades, there are numerous Nobel Prizes associated with this technique for getting structures of molecules. But unfortunately, there are many molecules of biological interest that people have no idea how to get them to crystallize. And then we need alternative techniques, and cryo-EM is one of those alternatives. And in cryo-EM, what you do, instead of crystallizing the molecules that we don't know how to do, we just freeze them in a very thin layer of ice. So the ice layer is very thin, and it is so thin that if you look at it in the vertical direction, you'd see one molecule or no molecule at all. And what you see here is like an artist's concept of the imaging process. So you have the ice layers, and you have 3D molecules embedded in this layer. And we'll assume for now that all molecules have exactly the same structure, and they only differ one from another in the way they orient themselves in 3D and also in their positions. And then you take projection images using an electron microscope. So you beam electron through the ice layer, and here you have a film detector or a camera, and what you get are 2D projection images of the 3D molecules. And so then you have a micrograph, and you have to box out or do particle picking, and then you end up with 2D projection images from which you want to find a 3D structure. Particle picking here seems a very easy task. This is just artist's concept. In reality, the level of noise is much, much, much higher. Okay, so we can model this mathematically as follows. So we have a molecule that we don't know its structure. And what we really are after is the electric potential created by the molecule. So the molecule is made of a bunch of charged atoms. And so with every molecule that we get its image, there is some rotation matrix, a 3x3 rotation matrix in SO3, and that basically dictates how the projection image would look like. And the projection image is just a line integral in the direction of the third column of the rotation matrix, plus some noise. So this is going to be our basic model. So basically what we measure is also known as the X-ray transform. This is a slightly different version of the radon transform, for those of you who know tomography. And the cryo-EM problem is an inverse problem. What we are after is the electric potential created by the molecule from these noisy projection images I1 to IN. Now, this inverse problem is more difficult than the usual medical imaging inverse problem, in which one, say, needs to do a CT scan, say, on the brain, and the patient would be told not to move for the duration of the imaging process, so that the machine knows exactly the directions of the views. In the cryo-EM problem, the directions of the views or the rotation matrices are also unknown. So in some sense, we have to invert an operator, but we don't know what is the operator that we need to invert. So obviously, if we can somehow estimate the rotation matrices, then it's a classical inverse problem in medical imaging or in tomography. So you can ask me, like Tom asked me over lunch, so okay, why don't they just tilt the specimen, the ice layer, and take another set of projection images? And then the relationship between the rotation matrices will be known. So this is actually something that is done, and this is called electron tomography. And the reason why we don't do it here is that we basically sacrifice resolution by doing so. So when electrons go through the molecule, they are so highly energetic that they break the chemical bonds of the molecule, and you destroy the fine features, the high resolution features in the molecule. So really the name of the game is to get to a reconstruction at atomic scale. That is what expert crystallography can achieve. And so that's why we're doing what is called single particle cryo-EM, just one image per molecule. Any questions so far? Okay. So this is just to illustrate and to see that we're all talking about the same problem. So suppose that I give you 12 projection images of this Disney creature, and your problem is to find the 3D structure.
But you get not just one molecule, you showed several.
Right, but we assume that the structure of the molecules is exactly the same.
But the orientation are the same too?
The orientations are different. So it's like I'll try to reconstruct you by taking an image from here, and then an image from here, and then maybe an image from there. But I assume that you haven't changed. Okay?
Yeah. But no, you assume that the molecules are all oriented in the same way?
No. So if I can do that, then I can do crystallography. If I have a physical way of getting all molecules to stand up in the same direction, then I can do crystallography. This will be a completely different talk. Right. So I take projection images at random directions because we assume that the molecules at the moment of freezing just pick some random direction. Okay. So the classical problem.
But you use not just you use all of that information on that.
Right. So I have many images. So here I'm showing you only say 12 images of the same molecule at different projection directions. And I'm asking you, okay, now find for me the 3D structure.
And these different projection direction come from, you had 12 different pictures.
12 different pictures, but of the same structure.
Yeah,
okay.
You don't know the orientation. The relative orientation is unknown.
Right. We okay? Good. So, okay, so here maybe you can get some rough idea of what is actually being pictured here. So from some of the images, you can make some clever guesses. But in reality, the images are very noisy. Okay, so this is just 4 images out of a much larger collection of 20,000 something images, like real microscope images. And like I just said, the reason why they're so noisy is because people try to not to use too much dose, too much electron dose. So if you're using too much electron dose, the images will be much clearer, but you're going to lose the high frequency content of the molecule. And so now the question is, I show you 20,000 such images, give me the 3D structure. So that's the cryo-EM problem. Okay, so for those of you who laugh and think this is going to be impossible, I'll show you what my students can do. Okay, so in this movie you see 2 structures superimposed, one in yellow, one in white. The yellow one is true structure, so it's a subunit of a molecule called the ribosome. In 2009, the Nobel Prize in chemistry was awarded for to 3 people, and one from Yale, one from Weizmann. And actually, I show you here at a low resolution, so that you can actually see the features in the molecule. And I didn't tell you what is the white. The white is our reconstruction from the same experimental 20,000 something images, noisy one that I showed you before.
Which were the ones you showed us in the previous slides.
Right. So the signal is there. And as you can see, there is nice resemblance between the white structure and the yellow structure. It's not atomic resolution. So what you see here is about 10 angstrom resolution. But I now hope that you believe that the cryo-EM problem is solvable to some degree. So we know from X-ray crystallography, like I just said, the 2009 Nobel Prize to Steve Stites and Ada Yonat. Yeah, I think I mispronounced the name for those of you who are recording.
So they managed to crystallize this particular structure, so they have an alternative route.
Yeah. So we just low-pass filter it to a resolution that you can see the resemblances. Okay, so how cryo-EM is actually being solved in practice?
And you want to know more than the shape, or do you want to know more than that, like the electronic structure, or not?
So we want to get, so electronic structure would be even finer resolution. So we want to get to like, say, 2 or 3 angstrom resolution. That would be very nice, because this will be like atomic scale, and biologists can then infer whatever they want about the molecule. So, there is some algorithmic pipeline that we have to use to solve cryo-EM. Usually people will just start from here, from iterative refinement. The previous steps are, okay, one has to do particle picking, what I just showed you, to box out particles from the big micrograph. And then if you have so many images, you can try somehow to find images that were taking at roughly the same viewing direction. So such images should look the same up to noise and up to in-plane rotation. So if you can identify such images, then you can average them after registration, in-plane registration, say rotation, in-plane rotation translation, and get rid of the noise to amplify the signal to noise ratio. And then you have to do orientation estimation, and I'll tell you in a second how this can be done. And after you estimate the rotations, you have to do a 3D reconstruction, and that's the classical tomography problem. And once you have an initial model, then you can iteratively refine it. That is, you can reproject it to get 2D projection images, and from those 2D templates, now you can try to match from the experimental images to the ones that you reprojected, and now you reassign viewing directions and rebuild a new model and repeat this process. It's not clear that iterative refinement will actually converge to the actual ground truth or something close to it. And it may highly depend on the initial model, and that's why people seek for good initial models. Okay, so
melting and refreezing while it's over there.
okay, so once you take a single image of the molecule, basically you destroy the molecule. So it's like in Mission Impossible, the movie. So once you hear the message, that's it. It is no longer there. No, it's no longer at our disposal. Okay. So how can we solve the cryo-EM problem? How do we get our intentions? So there is a fundamental theorem in tomography, the most important probably theorem in tomography, that tells us what is the geometry of this problem. This is called the Fourier projection slice theorem. And the slice theorem says as follows. On the one end, you have 2D projection images for which you can take the 2D Fourier transform. So here is a projection image, say the ice projection image, and I can take its 2D Fourier transform. And I show you here only the modulus because it's difficult to show complex values. And on the other end, you can look at the 3D molecule and consider its 3D Fourier transform. What the slice theorem says, it says that the values of the 2D Fourier transform are nothing but the restriction of the 3D Fourier transform to a central plane, a plane that goes through the origin and is perpendicular exactly to the viewing direction. And that's how CT works in medical imaging. You get projection images. You can take the 2D Fourier transform and then populate the 3D Fourier space with planes that go through the origin. And once you have a large enough planes that cover the 3D Fourier space, then you can take 3D Fourier, the 3D inverse Fourier transform and get back the density in real space. Now, in Cryo-EM, this geometry holds. We have planes that go through the origin, but we don't know how they are oriented. So we need to organize somehow the planes so everything would make sense, so that they would agree with the actual views. And so, like I told Tom before, there is a high school geometry that comes into play here, that we know that every two planes in 3D, unless they are parallel to each other, they are going to intersect at a line. So this is called the common line of intersection. So this means that in the 2D Fourier space, there is going to be one line, say one radial line in image I, the Fourier transform of image I, and one radial line in image J, so that the values of the 2D Fourier transform agree on that line. So you can find that line, say, by using methods of some normalized cross correlation. And then you know the relative orientation between the two planes up to the angle between them. So there is still 1 degree of freedom left. Yeah?
So is the top line, both of them are 3D Fourier?
Right. So here, this is 2D projection, 2D Fourier, 3D Fourier.
What are the spokes in the 2D Fourier?
This one?
Yeah.
Yeah, it's just what you get when you do the Fourier transform.
Sorry, so it's not the colors blue and yellow that we see in the background?
Where?
So the background is blue and yellow, right?
Here or here?
In the middle. So
Here?
there's two superimposed images here, right?
Here?
Yeah, in the middle.
In the middle?
All the spokes, the blue and red spokes.
Yeah.
There's the values of the Fourier transformation, or at least the amplitude.
Right.
So what are the spokes?
So this is the amplitude of the Fourier transform, and this is a line where the two agree.
Oh, so it's just a point of reference from you?
Yeah.
What the orientation is? Okay.
Right. Okay. Yeah. Sorry if it's confusing. So, in order for us to actually determine the rotation, so like I just said, we still have this 1 degree of freedom that is unknown. We can determine it by adding a third plane. So from the common line of intersections between 3 planes, we can uniquely determine the relative orientations. And of course, you can add a 4th, 5th, and so on. Now, of course, this detection of common lines is not an easy task in practice due to noise. And so one would like to find an assignment of orientation that is consistent as possible with the noisy data. Now, this is a huge problem of its own, and I'll actually not speak about this today. I just wanted you to see that one can actually solve the Cryo-EM problem in terms that there is enough geometry that one can use in order to find the orientations and to get a molecule. So this is hard enough problem, but I showed you a movie. I'm telling you how this can be done. I hope that you're at least somewhat convinced. Now I'm going to talk about the real challenge that we are facing. And the real challenge that we are facing is called the heterogeneity problem. And just like Joe asked me before, is it the same molecule? Is it the same structure? And usually the answer is no. So we know that molecules, they change their structure with time. So for example, protein channels, they have an open state or they have a closed state in which they let ions go through or don't. Or we have, and there can be all sorts of variability in the 3D structure of the molecule. So this can be a discrete type variability, that you have, say, 2 dominant states or 3 dominant conformation states, or it can be some continuous even deformation. So some part of the molecule maybe can be flexibly moved from one side to the other. And so in real data set, the assumption that we have exactly the same structure of the molecule over and over again does not hold. And it actually, usually this variability in the structure is what the biologists are after, because then they can infer something about the function of the molecule. So if I tell you, okay, the molecule looks either like this or like that, then there must be a reason why it changes its structure and have a different functionality for these two different states. And then you can do biology. But if I just give you some average 3D structure, it's much harder to now understand how the molecule functions. So biologists are very interested in this structure of variability. So what is the problems we are facing? We have the same 2D projection images like before. We still have just one molecule, one image per molecule. But now molecules can actually look different from one to another. So if you thought before that the cryo-EM problem is challenging enough, okay, and you didn't believe that it's possible, now it's even more challenging. That is, we are trying to not recover just one structure, but many structures from the same data set. And we don't even know which projection image corresponds to which volume. So even if I tell you, okay, there are only two states, usually we don't even know how many states there are. But even if I tell you, okay, there are just two states, state A and state B, you look at the projection images, you don't know if they come from state A or they come from state B. So there is some classification that one needs to do here, even before doing the 3D reconstruction. Now, so that's one challenge. The other challenge is that
Can I think of these molecules as being like a protein, or?
yeah, think of it as a protein. Yeah.
So once the protein's folded, presumably you have it in its folded state, right? That you'd be looking at it, as opposed to.
Yeah, but there may be several folded states. So a protein may fold, and then it can change its conformation to a different state.
So there could be several.
Right. The energy landscape, say, of a protein can be very, very complicated, and it can jump from one state to another.
And still be folded. I mean.
Yeah.
These foldings are, as I understand, they're fairly tight foldings, right?
Yeah, but like I'm saying, there can be several states. Not just it can stay for a long time in one state, and then switch to another state rapidly. So, yeah, so just like I said before, for example, I think the most famous example is protein channels. That they have an open state, and they would close them and not let anything go through. And then they would open again.
But you don't expect this will happen during your taking one image?
So I expect my sample of molecules to belong to have several. And I don't know what's the proportion, how many states there are. I know nothing. So if, say, we did everything and reconstructed an average volume, let's say, now to understand the variability, we can reproject that volume and remove the mean, remove just the contribution of this average volume. And what we'll be left with is, if you think and remember the noisy images that I showed before, now suppose that I'm removing the contribution of the average, you're left with something that looks very, very similar to just pure noise. Because even though there was this tiny signal there, now I've removed it. So the challenge in the heterogeneity problem is that even with conventional, compared to conventional single particle reconstruction, now we have to solve this problem at a much, much lower signal to noise ratio. So we may need lots and lots and lots of images, much more than we use for just doing classical SPR. Okay, now people in this field are not afraid of challenges. And so there are these several techniques for dealing with the heterogeneity problem. And 3 of them are listed here. One is called bootstrapping using resampling. What they do in this method, let's say we have 100,000 images. So they will randomly select, say, 10,000 of them and assume that they belong to, say, one conformation and build the structure.
These 100,000 images are from one shot of the X-ray?
So you get several micrographs. In a micrograph, you have, say, hundreds of particles. You have to collect many micrographs. And so you do resampling, and every time you reconstruct a new volume. And so now you get different volumes, because every time you resampled different images. And now what you do PCA for the 3D volumes that you get.
Do what?
Principal component analysis. And
What is it called again?
principal component analysis?
Yeah.
Okay, PCA. So the idea is to construct the covariance matrix associated with the 3D volumes that you reconstructed, and then to look at the leading eigenvectors of that matrix. And they will give you the directions of maximum variability of the data set. In our case, the 3D volumes. Now, so for example, if there are just two states, then the principal component would give you just the direction from one volume to the other, just the difference of the two volumes. Now, okay, I'll mention in a second what's the problem with this bootstrapping approach. Then there is a method which is called maximum likelihood, and then you say, okay, I'll just throw in as many parameters as I want and try to learn them from the data. So I try to fit the number of states that there are. I have to come up with some underlying distribution for the conformations. So they usually do some Gaussian type modeling. So there are many, many, many parameters that they try to fit, and then you have some optimization problems that you have to run. It's very, very slow, and because there are so many parameters, and nobody knows if it will converge or not to the actual solution, because there is no convexity or anything like that you can actually assume this problem. Question? Okay. A third method, due to Shatsky and Malik, is to do some kind of spectral clustering using the common lines. So if you take two images, then if they actually belong to the same conformation, you expect that they will have a good agreement on the common line. And if they come from different conformations, you expect that they won't have a good agreement on the common line. So now you can build a graph whose vertices are the images, and the weights on the edges correspond to how well they agree on the common lines. So that's the method that Shatsky and his collaborators came up with. Okay, so you can say, okay, so there are already these three approaches. They sound.
What's JSB stand for?
Journal of Structural Biology.
What's structural?
Journal of Structural Biology. Right. So you can ask, okay, so why do we need more methods? I mean, they're already trying to solve this problem. So I'll mention some of the deficiencies of this problem. So the method of resampling, the issue is that the 3D structures that you build by sampling images, they do not correspond to any real volume, because we sampled from different conformations, and then the reconstruction that you have is not some linear combination of different volumes, because you have to do.
You use the word volume to mean shape. You use the word volume.
Volume, yeah.
That's shape. You mean?
By volume, I mean the electric potential phi of x, y, and z.
Oh, that's volume. It's potential.
Right. In imaging, we usually call volume to a 3D array of numbers, because one has to discretize this function of three variables. So we call it a volume.
Nothing to do with the volume of the molecule.
No, it's not related to the actual volume. Yeah, so the terminology is a bit different, yeah. So in resampling, you get 3D structures, but the 3D structures actually correspond to nothing, because they're not any linear combination of actual volumes, okay, or actual electric potentials. And so, and also you don't know, when we resample, resample again from the same images. So it's going to be some dependencies, and then you do PCA. Who knows what you're going to get in this method? In the method of maximum likelihood, like I mentioned, this is extremely slow, because there are so many parameters, you have to come up with some a priori distributions, and nobody knows what they are. And in many cases, it actually fails after you run it for a few months on a computer cluster. And you don't even know when it converges, does it actually give you the right answer. The method of common lines, the problem with that, it actually does not exploit the entire information in the images. It only look at the consistency on the lines themselves. So instead, we'd like to come up with an algorithm or a method that first of all, we wanted to say, okay, provably will find us the conformations, their number that we can reliably detect from the noisy data set. We want it to be fast, and we want to say to the biologist, okay, if you need this number of images at this level of SNR to get the variability in the data. Otherwise, you have to now collect more data and come back. So we want something that is provable, fast, and have a low sample complexity. We want as fewer number of images as possible. So to make progress with this problem, we'll make some assumptions. The first assumption that we'll assume that the variability is small.
That means the molecules don't change.
Right, they change, but they change a little bit. So
How much do you know about the chemical composition of these molecules?
oh, you know exactly the chemical composition.
You know the full chemical composition.
Yeah,
So it's just the conformational that you're looking at.
just. Yeah.
When you say the variability is small, do you mean that two different variants are very similar, or do you mean that there are a small number of different variants?
No, so I mean that the change in the structure from one conformation to another is small.
That should make life harder, right? If you have, let's say, two different structures that are completely different, wouldn't it be much easier to tell them apart?
Maybe, but I want to make my life harder, and but you'll see that it's actually convenient to make this assumption. So for example, this can be that the two conformations that look exactly the same, but maybe at some part there is some change, that some localized variability. So why do I need this assumption? Why it makes my life easier? It makes my life easier because then I can say, okay, let me just reconstruct one single molecule at first and assign rotations to all the projection images that I have in my data set. And then I can assume that actually the projection directions, the rotations, are estimated quite reliably. And then I just need to solve the classification problem. But from now on, I can actually assume that the rotations themselves are known. Okay, so I did either common lines or iterative refinement, and I get the rotation matrices. And because the changes between one conformation to another are not so great. So actually, the rotations are estimated reliably. But now we have to deal with the classification problem. And the approach that we'll take is the same approach in resampling, where one wants to do covariance matrix estimation and PCA, principal component analysis, for the 3D volumes. But I'll show you that it's possible to do estimation of the covariance matrix directly from the 2D images without building any 3D molecule in the process. So again, so usually when you have to do PCA, you have a data set. You have to build from the data set the sample covariance matrix, and then you look at the leading eigenvectors and eigenvalues of the covariance matrix. In this problem, if I want to mimic this approach, I have to, and I want to do PCA for 3D volumes, what I need to come up with is some 3D volumes to actually do PCA to the volumes. But I'm saying no. I'll show you that I can actually estimate the covariance matrix of the 3D volumes directly from their 2D projections. And some of you can start waking up. We're not there yet, but you can raise your head. So in PCA, so that's probably one of the most, or the most popular tool in multivariate statistical analysis if you want to do dimensionality reduction, compression, or denoising of your data set. And the usual setup is that you have n data points, say in a p-dimensional Euclidean space, and you assume that there are independent samples of some random vector x, so IID samples, with some mean mu and covariance sigma. And what you do is you have a sample analog for the mean and for the covariance. So you build sample mean and sample covariance matrix. And then you look at the sample covariance matrix, and you compute its leading eigenvectors, the eigenvectors that correspond to the largest eigenvalues. These give you the principal direction, that is, the direction in which the data changes the most, the direction of most variability. And then you can use them to do dimensionality reduction, compression, denoising, and so on. So that's classical PCA. Okay. Now, why is it useful in our problem to think about PCA? So for example, if we have just two conformations, so the number of heterogeneous groups is just 2, then how many principal components we expect to see? One, right? Okay, so there will be an average, the mean, and the principal component will just be the difference between the two volumes. So in that case, sigma, the covariance matrix, should be low rank, and the principal component solves the problem. Once I know the mean, the average of the two conformations, and I know their difference, I know the two structures. That's it. We declare victory. And similarly, if you have, say, k conformations, then the number of leading eigenvectors should be k minus 1. There should be only k minus 1 eigenvalue, so it's, again, a low-rank matrix. And how do I then can do classification? Well, we take the electric potential of a given molecule. We know that we can write it as a linear combination of the eigenvectors plus the mean. So if we look at the projection image, all we need to do is just to project the volume. So it's a linear operation, and then add noise to it. And then we can extract the expansion coefficients using least squares. So for every image, I can then associate coefficients ak, k of them, or k minus 1 of them, by just do a least square fitting. And then I can look at the k minus 1 dimensional space of coefficients and just solve the clustering problems there. So, and problem is solved. So I can do k-means or spectral clustering, whatever you want. But once, the major step here is just to do the PCA. How can I come up with the covariance matrix? Okay, so I just want that we all agree that doing once I have the covariance matrix and I have its eigenvectors, doing classification is a piece of cake. Okay, but the question is how to actually get the covariance matrix.
You have a sample covariance.
Right, sample covariance, right.
You compute that, though, or do you?
I have to show you how I do that.
Okay.
Yeah.
Typically, what's the number of samples compared to the number of variables?
More than, if you give me 100,000, I'll ask you, okay, now give me another 100,000. Okay. So the more the merrier, right? The more images, we can do a better job in estimating the covariance. Okay. I'll try now to show you some analysis that will answer this question.
But how many pixels is one image?
Usually 100 by 100 or 300 by 300, something of that order. So pixel size can be 1 angstrom by 1 angstrom or 3 angstrom by 3 angstroms, and based on how big is the molecule you try to reconstruct.
So each pixel has a degree of grayness on that.
Right. So every pixel, say, you'll have a number between 1 to 200, or 0 to 255.
So you're trying to get, is it a finite rank matrix you're trying to reconstruct?
Right. Hopefully finite rank.
The problem is now this x1 to xn, you don't really know what they are because you only have two-dimensional projection.
Right. So I want to do covariance estimation from projections of data. Exactly. So
How many pixels would be a good image? A good 3D reconstruction.
so if an image is 100 by 100, the volume would be 100 by 100 by 100. So the dimension would be like 1 million. which means that the size of the covariance matrix will be 1 million by 1 million. So we also have to think how to do computations smartly, because no one wants to store a million by million matrix and do operations with it.
But the 100 by 100 by 100 in space would be good resolution for the result.
Right. So you see that this is a tough cookie, this to get this covariance matrix. Okay, I'll mention some of the problems soon. So okay, so we saw resampling. We want to do something better than just resampling that does not suffer from dependencies, and we want something with theoretical guarantees. Okay, so I told you already once what is the major, most important tool in tomography. That was the slice theorem. And now we're going to use it again. So I claim that the slice theorem enables us to estimate the covariance matrix directly without resorting to 3D reconstruction. And the idea is fairly simple. So instead of working in the real domain, I'll be working in the Fourier domain. That is, we are now all going to think about the covariance matrix of the molecules, but not of the molecules of the 3D Fourier transforms. Which means that, what does it mean that I need to get the covariance matrix? I need to get the covariance between any two frequencies now. Okay? So Tom chooses two frequencies, and he asks me find the covariance between them. So he gives me the two frequencies, and now I know that there is going to be a plane that goes through these two frequencies and the origin. 3 points determine a plane. So I'm going to look at all these planes that correspond to those two frequencies. And because of the slice theorem, I see now
What does frequency here mean?
a point in the 3D reciprocal space, in the 3D Fourier space.
Nothing to do with time frequencies.
No, so here is spatial frequency. Okay? And so we're going to look at all those images and just correlate the values of these two frequencies, because we know from the slice theorem that when we look at the images, we know what are the corresponding frequencies in the plane are now lifted to frequencies in free space. So by doing so, I can now populate the entire 3D covariance matrix. For any two frequencies, I can find the corresponding planes and now generate the entire 3D covariance matrix. So that's the basic idea. There are going to be problems with this basic idea, but I just want to make sure that we are all agree on the basic idea. Okay, so what it shows that we can actually do that. I don't need in this process to reconstruct any molecule. I'm just using the slice theorem, populating the entire 3D covariance matrix, and then I can proceed with PCA. Okay, so this slide just summarizes what I just said. Once you get the covariance matrix and the mean in the Fourier space, then all you need to apply is to apply the inverse Fourier transform. The covariance matrix is just conjugation from left and right with the Fourier transform. You can still, once you estimated the covariance matrix in the Fourier domain, you can get it also in the real domain. Or alternatively, because it's a unitary transformation, the Fourier transform, you can just compute eigenvectors, and there will be the Fourier transforms of the eigenvectors in the real domain. Okay, so, but that's not the whole story. So there are actually many, many important issues with this basic idea. So there are some limitations. The first one is that there is interpolation error. Okay, so when you give me two frequencies and say they correspond to some discretized frequency, that is, we have to use some discretization of the 3D Fourier space, we're not actually going to find exactly planes that go through these frequencies. We're going to get planes that get us close enough. And so we'll do some nearest neighbor interpolation. And by doing so, we introduce some error. And this error is going to get larger and larger as we go to high frequencies, because then just imagine like planes that go and start deviating from one to another. So getting the high frequency is going to be more challenging for us. We're also going to have statistical error. That is, if we'll try to estimate the covariance matrix in this way, then the number of planes that go through a pair of frequencies is not the same for every pair of frequencies. For example, if you take two frequencies that are on the same line, then we actually know that there are plenty of planes that go through the same line. It's the common line property. So such frequencies will be much more accurate. We can get much more accurate estimations than compared to others.
You mean two frequencies going, a line that goes through the origin?
Right.
Okay.
Right. So if you have 2 points that together with the origin that are on the same radial line, then I can get them to much better accuracy compared to any other covariance matrix element. And then if I do PCA, just compute eigenvectors, eigenvalues, it doesn't take this into account at all. And also if I look at 2 high frequencies, there are going to be very few planes that are actually going to go through them, whereas if I take 2 low frequencies, now I can find many more planes. So I have to somehow take this into account. Then there is the question of sample complexity. How many images do I really need? Can we somehow, if I look at the spectrum of this sample covariance matrix, can I tell the signal eigenvalues from just eigenvalues that are due to noise? Because, okay, we have to tell the biology, this is true variability of the molecule, this is just due to noise. It's an artifact, it's not really there. We want to tell them how many groups are actually there, and so on. And then there are the computational issues. So like Yanni said, okay, the volume is million dimensional, so now you're going to build a million by million matrix. So you're going to actually store it on your computer. This is going to require something like 4 terabytes. And you're going to tell me that you have enough time to actually generate, store it, and compute eigenvectors? I don't really believe you. Okay, so we need to also address this issue as well. So we have to address each of these limitations one at a time. And some of the solutions are going to apply to the other issues. So for the interpolation error, we're going to throw out this Cartesian basis and represent our volumes in a different basis. And so that we also agree with the Nyquist sampling criteria and so on. I'll get to it soon. Once we change the basis, also we have to understand how we deal with the statistical error, because now the projection operators are no longer just restriction of the 3D volume to a plane. Once we did the change of basis, then the projection operators also change. We have to address the sample complexity, and this will lead to a pole in random matrices. And we also have to address the computational cost. Based on the time that I have, I'll see which one we focus on first. Okay, so how we represent the volumes? We use spherical coordinates and spherical harmonics, radial functions. For the radial functions, we use spherical Bessel functions. And these are useful to represent structures that are compactly supported. And we have a criterion for which terms in this expansion we need to take, so that we're not trying to represent artifacts that are not really there. That is to obey or satisfy the Nyquist criterion. So let me skip that. All it means that now instead of volumes, phi 1 to phi n, we represent them using vectors in a p-dimensional space. But these vectors are just the expansion coefficients of the molecules in this new basis. They are no longer just the values on the Cartesian lattice. So we have these volumes, but now think of them as just p-dimensional vectors. And they are sampled from some distribution of the conformations. And so we have a mean, we have covariance that we want to estimate for that distribution. In reality, what I really want to do is to characterize for you the entire distribution of conformations, but that's probably too much to ask. So let's be modest and just try to get the first and order statistics. So phi 1 to phi n, we have n molecules, and each one may be different. In the classical cryo-EM case, all of them are just the same. But now they may be different, and they are sampled from some distribution. And you can think of it just as a distribution for the p-dimensional vectors, the vectors of the coefficients in the new basis. Right, the relative potentials. So there are, say, functions in some L2 space, but these functions are sampled from some distribution over this L2 space of functions. P is the number of coefficients that I use to represent these functions. So I need infinite number of coefficients, but okay, because my images are finitely sampled, there is no hope to actually get functions in L2, right? So there is going to be some discretization. And so
L is the number of Fourier coefficients you're keeping in this.
exactly. Right.
But I mean, how do you compute the potential from a given molecule, from a given orientation? You know, the charges on some sense, so you take.
So at the end, I'll get phi in this way. If you really want now to find the location of the charges, then you have to invert the Poisson-Boltzmann equation. But we'll not do that here. So I'll just find the electric potential, which is what
But
the
the electric potential is due to the charges, no?
right.
So you have to know where the charges are.
I'll find the potential, and this will tell me where are the charges.
But the X-rays, they don't measure the potential, do they?
They do.
They don't measure the positions, they measure potential.
Right. The electrons, their phase is changing due to the electric potential.
It's an electron.
Right.
It's not an X-ray.
No. Okay. So in our model, the case image that we get is a projection of the case molecule plus noise. And so now the question is how to find the covariance matrix of the x's from the images. And we'll assume that noise is just Gaussian. Now, remember that we don't know what is the distribution. It's not necessarily going to be Gaussian. So we're going to do something that does not impose any underlying distribution.
So it's Gaussian, but you're not specifying the covariance of the Gaussian.
So only the noise is Gaussian. But I don't know what is the distribution of the x case. This may be non-Gaussian. For example, if there are just two states, it's just a discrete distribution of two values. Yeah?
So you assume that this error comes from this projection, not from the molecule itself.
The
Projected is then plus the error.
You mean what is this epsilon?
Yes.
This comes from the imaging process itself, the epsilon.
No.
The error. Remember the very noisy images that I showed in the beginning? That's the noise.
Yeah, but instead of px plus epsilon,
Right.
the px then plus epsilon.
Right. Px plus epsilon. There is no parenthesis here. Okay?
So the random part is in the x itself.
No. So there are two randomness. One in the x itself because of the variability. And one in the epsilon, that's the noise, independent of the x. What we are after is the sigma of the x's. Okay? I'm telling you I know what is the sigma of the epsilon. It's just diagonal. Sigma squared times the identity. Okay? So I know the statistics of epsilon. I don't know the statistics of x. And that's what I'm after. I is observed. Everything else is unobserved. Okay? So let's do a very easy first-year statistics calculation. What is the mean of I? The mean of I is just pk times mu, the mean of x. Mean of epsilon is 0. That was easy. Another exercise, what is the covariance of the case image? Well, we just subtract its mean, multiply by the transpose, takes the expectation, and because noise is independent of the volume, we just need to add the two covariance matrices, sigma squared I due to noise, and p sigma p transpose due to the variability of the molecule. Okay? So we want sigma and we want mu. So the way that we'll estimate them, we'll try to make the difference between this guy and this guy as small as possible. So we look at ik, we look at the expected of ik, pk mu, and we try to make this difference as small as possible across all possible images. That's least squares formulation. And similarly for sigma, the way we estimate sigma, we look at this guy. We know that this is going to be the expectation of this guy, so they should be close. So the way we'll estimate sigma is by just, again, minimizing a squared loss function. And this is just the Frobenius norm of this matrix. Okay, so these are just least squares problem. We can solve them and get linear equations that mu and sigma needs to satisfy. The equations that we get are this pair of equations. Now you see that the equation that the average mu, the mean mu satisfies, is just a classical equation in tomography. What you have to do is you have to back project. P transpose is called the back projection operator. You have to back project the images and then solve the least squares. You have to invert this matrix. And once you have enough images, this operator is going to be invertible. It's going to be non-singular, and you get mu.
Is it completely obvious that the noise has this sigma square identity for random? I mean,
it's not just that it's not obvious. It's actually not true. So, so usually what we do for the images.
Is it reasonable? Right.
So before we actually process the images, so the noise is colored noise. It's not white noise. And so before we process the images, we actually pre-whiten the images. So we try to estimate what is the power spectrum of the noise, and then apply a filter that would make noise white. And then we start this whole procedure. Okay, that's why you can assume that noise is
Because you can calibrate the
right.
the instrument or
Right.
whatever, so it comes from past.
Right.
Okay.
Okay.
So I'm a bit confused because I thought you don't know PK either. You know PK?
I know PK because I told you. That's why I assume small variability.
You've estimated that in the previous step also.
Right. So we estimate the mean. You see that estimating the mean just means that, okay, so we need the PKs to estimate the mean, but I'm reconstructing an average structure that also gives me the rotation matrices.
And
Okay.
sigma square is known as well.
Sigma squared is also known. Okay. Now we look at the second equation for sigma n. And you see that sigma n also satisfies a linear equation. The right-hand side is completely determined from the images and from our knowledge of the projection operators. The left-hand side, you see some linear operator applies to sigma n. So it's a linear operator when one thinks of sigma now as an element of a linear space. Okay, say a p squared dimensional vector space. Okay, so you see that mu n is just what we said, the reconstructed volume, as in the homogeneous case. And for sigma n, well, if there were no projections, then we just get the usual sample covariance matrix. But you see that because there are no projections, we have to do this inversion of this operator. But you see that even if it was not a problem in tomography, even if you are talking about a completely different data set, and the data that you observe is just projections of some underlying say, true physical features and so on, and you observe the data through some lens that does not allow you to see the entire features, but only few of them or some linear combination of them, still you can end up with this linear equation from which you can estimate what is sigma. So this is related to what people sometimes call matrix completion, that I see only a few of the matrix entries and somehow I can now fill in the entire matrix.
Two questions. The first one is, when there's no projection, that's the empirical covariance matrix up to the sigma square identity correction, right?
Right.
Okay, and then are you going to need some assumptions on your PKs to be somewhat spanning everything?
Yeah.
All right.
If not, then I can not even get the mean.
Yeah, but you could get some projection of all these things, right? So you could get a partial inversion of that.
Yeah, but you need this, at least this to be invertible. Otherwise, you cannot proceed.
So, just a question. In the second optimization, so sigma is actually has some symmetry structure, right? Like PSG structure. So the second optimization, it's not a free variable.
Right. So sigma needs to be PSD,
Yes.
positive semi-definite, because it's a covariance matrix.
Right.
And due to practical reasons that we want our algorithm to run in a reasonable time, we throw this condition. We don't want to deal with it.
Okay.
Right. And later you'll see that in any case, we're just interested in the eigenvectors corresponding to the largest eigenvalues. So if these are estimated well, we don't actually care about all the rest. Okay, so some basic things that we can prove. For example, the estimator for mu n is unbiased. If n is large enough and this is invertible, then it's unbiased. More importantly, both sigma n and mu n are asymptotically consistent. That is, when n goes to infinity, both mu n and sigma n just converge to their population counterparts, to the true mean and the true covariance. So that's great. The more images you give me, I'm getting closer and closer to the true value. So now I can declare victory and go home, but not really, because in reality we don't have so many images that we actually at the limit. Remember that P is very, very large itself. This is the million by million parameters that we somehow need to estimate. And so we cannot really assume that we are in the classical statistics regime where n is much larger than P. And so we're really in this, more or less this regime where n and P are more or less of the same order. Okay, so again, that's the fundamental equation that we are looking at. And we said this is a linear operator that acts on sigma. I will not show you now how we do it, but we actually have a fast algorithm how to invert this operator L. So it turns out that in this new basis, if you look at the continuum counterpart of L, that is, you take the limit of infinite number of images, and the rotation matrices are just uniformly distributed according to the Haar measure over SO3, then you end up with this integral operator for sigma. So this integral operator is just the counterpart of projection, back projection that you have in classical tomography. But now instead of operating on our original object, when we try just to reconstruct mean, now we have to reconstruct covariance. So I submit that this is the true operator that is of interest to look at. That's the mathematical object that we should investigate. Okay, and so some basic properties. For example, it's a positive semi-definite operator over this space of covariance matrices. It commutes, of course, with rotations because we do integration over the entire SO3. And in this new basis, it has some interesting block diagonal sparse structure that allows to do the fast inversion. So we also call it the projection covariance transform. And it's important to understand this operator, just like it is important to understand projection back projection in classical tomography. Okay, so now we get finally to the random matrix question. So sigma n, our covariance matrix, satisfies this equation. That's how we estimate it. Now, the first thing that you try to understand when you do PCA with noisy data is just what is going to be the distribution of the eigenvalues when you only have noise. So this means that sigma is 0, there is no signal, mu is 0. So we want to understand first what is here on the right-hand side. So this means that you have only noise, epsilon k's, that you project and back project. So the epsilon k's are noise in the images, and then we lift them up to the size of volumes. And you want to understand properties of this random matrix that naturally appears in this problem whenever you have to deal with projection of data and not just data directly. So this is just a matrix of a sample covariance for y's that are defined as the back projection of the epsilon k's, right? So what you have here is yk times yk transpose. And so, yeah. Right. So epsilon is noise independent of x, also independent of the rotation. Yeah. So expectation of yk is 0. Expectation of the covariance of yk is sigma squared times expectation of p transpose p, projection back projection. So that's the classical operator in tomography. It's actually given by convolution with a filter. We know exactly what is this operator. For those of you who know about RAM filters, this is what's going on here. In the Fourier basis, it is diagonalized, and we know exactly the eigenvalues. So what you have here is a sample covariance matrix of random vectors whose covariance matrix is not identity, but a diagonal matrix in the Fourier domain. and we know exactly the eigenvalues. So actually, if you go back to the original paper of Marchenko and Pastur in '67, they actually treat this case in generality, and they derive the Stieltjes transform of sample covariance matrices in the limit where P over N goes to a constant for general diagonal matrices and not just for identity matrices. So in principle, one can understand and get the limiting spectral density of the matrix Sn. Okay. Now we want to understand something more, because our sigma n is not Sn, is Sn after we invert L. So now we need to understand what is L inverse of Sn. And that's a question that I don't know how to answer now. So basically, we have Sn, this sample covariance matrix, and now you apply to it a linear operator, but this linear operator is not just multiply this Sn by a matrix. You apply a linear operator over the space of covariance matrices. So it's going to mess up the entire matrix by taking some linear combination of all the matrix entries. Now, L is a deterministic matrix. And so the question is, what is the limiting spectral density where you apply a linear operator to a random matrix? But now the linear operator is over the space of matrices, not on the space of the underlying vectors that created the matrix. Okay, so that's a question for you. So let me just finish by showing you numerical results, what we can do now. So in the numerical, result is going to be a synthetic simulation. We play with two volumes. One is just a Gaussian density of this form. So that's in 3D. What you see here in A is just a projection of the Gaussian. And the other conformation is just going to be two Gaussians. So here is the first one, and we added another one that has a smaller size. And that's the mean of the two. So you can see that in the mean, this Gaussian ball now appears weaker. And that's the difference between them. That's the variability between volume B and volume A. And what you see in E is just original noisy projection, so you can still somehow see the two Gaussians. But in G and H, I removed C. I removed the mean. So after removing the mean, you can see now that the signal becomes much, much weaker. It basically disappeared. You don't see it anymore. And now we want to understand the variability from such images. That's the heterogeneity task. So here is what we can do. So here we use 10,000 images. And so this is a slice of the true volume. And these are slices of our reconstructions at different SNRs. Now that's a reconstruction of the mean, of mu. So for mu, we can do a relatively good job, you can see, even at low SNRs. Now we want to see if we can also reconstruct the heterogeneity, this top eigenvector. So this is the true difference. Just now black and white reverse their order. And that's our reconstruction of the eigenvectors at different level of SNR. So here we do a good job. Decrease the level of SNR from 0.01 to 0.006. Still we see it. Decrease it more, it completely disappeared. So what is going on here is the same phase transition phenomena that most of you are familiar with. So if I'm looking at the spectrum of my sample covariance matrix that I created, then at high SNR, you can still clearly see this one eigenvalue separated from the bulk of the spectrum. And there is a nice spectral gap. And as we decrease the signal-to-noise ratio, this distribution gets larger and larger, and the gap gets narrower. Still, there is some nice correlation value. But once the SNR gets below a threshold, then you don't see the eigenvalue popping out anymore. And basically, the correlation becomes practically zero. And we cannot reconstruct the top eigenvector. So from this spectrum of the eigenvalues of the asymmetric covariance matrix, we can tell the biologists reliably how many groups we can actually detect, just the number of eigenvalues that pop outside this distribution, pending that we can actually characterize this distribution. So we know how to characterize Sn, but now we also have this inversion by L. So that's why it's important to understand this spectrum. So we hope that the operation of L will be benign. That is, okay, we can just look at Sn and see if there are on the right-hand side and see if there are popping eigenvalues there, and hope that the inversion by L will not make a big difference. But that's a hope rather than a theory. So, and you can see also here in the what is called Fourier shell correlations. So these are correlations based on for each shell in the frequency domain separately. That for the blue and the red, for the highest NR, we do a good job. We get correlation 1. But here is the what corresponds to the green, to the lowest NR, which is below the first transition. Okay, so summary. So summary. So what I showed you that PCA is a viable method for tackling the heterogeneity problem in Cryo-EM. It actually works. And you can actually estimate the 3D covariance matrix directly from the 2D projection images without doing all sorts of heuristic approaches such as bootstrapping using resampling and so on. There is no need to impose any prior distribution for the conformations. You don't need to know anything about the a priori about the distribution of conformations. And the last part is that random matrices, they play an important role in solving the heterogeneity problem. And characterizing these distributions can give the biologists and the microscopists tools to actually understand how many structures, different structures are in the data. So thank you very, very much.